Okay, so in this video, we'll be discussing about differentiation and integration. Now, um, calculus is actually a prerequisite to this discussion, as I won't be teaching you differentiation or integration. Rather, I'll be trying to give you a new perspective to view these topics from a different point of view. So, let's write the topic of discussion, which is differentiation. Now, as nature of this video is very short, therefore I'll be only illustrating my perspective through very basic functions. And the most basic function that I can think of right now is y is equals to x squared. Graph of which is a parabola, as you guys might be already knowing. It's right. It'll be an upward opening parabola with its vertex at the origin, and it is upward opening because the coefficient of x squared is 1. Now if you differentiate this function dy by dx with respect to x, then you'll get 2x by simply applying the power. The kind of thing that I want you to take note of right now is, wait, let me make some space here. So the kind of thing that I want you to take note of right now is if we write this particular formula in this manner, then it won't make any difference, right? Okay, wait, before following along in this discussion, there's one thing that I want you to know before we move on to the juicy part of our discussion. And the thing is, every curve is made up of infinitesimal straight lines. So let me take my time to discuss this statement. The thing that I'm trying to focus on is that if you zoom onto any curve, then what you'll find at a very zoomed in scale is that every curve is just made up of a set of straight lines. Okay, so for example, if I just zoom on to this portion of our parabola and show you in there, then the parabola is nothing but a set of straight lines which are joined together in this manner. So every curve that you see is actually made up of infinitesimal straight lines, infinite of them joined together. Okay, now I actually have one illustration to show you what I mean. So I've actually made a program to illustrate to you what I've just said. So let me open my Jupyter notebook. Okay, I'm so sorry. I've spelled it wrong actually. Yeah. Okay. Wait for a while till it is open in my browser. Okay. This is the program that I've made. Okay, so let me run all the cells first. So I've actually made a a walkthrough of this programming along with the mathematics that I've used to create this program in my on my YouTube channel that you can see in a playlist called Code in my channel, where I have made a very detailed walkthrough of this program on what mathematics I've used to create this program and all, and the coding walkthrough and the code and the code walkthrough as well. So if you're interested in this program, then you may watch that video to create one for yourself as well. So let me start by a very simple polygon, a polygon of maybe 8 sides. So it's an 8-sided polygon, and I've just shown you this particular figure just to familiarize you with the kind of program that I've made. So it's an 8-sided polygon, and the amount of sides that I'll put in between between the parentheses, the matplotlib will generate a plot of the given sided polygon, a regular given sided polygon. So let me increase the sides to, let's say, 23. And what I want you to take notice of is the fact that as I am increasing the number of sides, as I've increased the number of sides from 8 to 23, in this form, in this portion of the graph, it's very hard to actually differentiate between the curve and the circle, right? I mean, between the lines and the circle, between the sides and the circle, right? In this portion of the graph, you can clearly see that you have these fine edges in here, but in this particular section, it becomes harder to see where the gaps are, where the edges are. Now, let's take it to an extreme and try out 47 maybe. Wait for it to compute all the coordinates. Yeah. Now, as you can see, at 47, it's on the left side of the figure. It is completely overlapped. You cannot actually differentiate between the curve and this. The polygon and the circle. Right. In here, in the right side, it's still visible. The gaps kind of are there. They're still visible. But on the right hand side of the figure, no, it is completely overlapped for the naked eyes. So let's take this argument, let's take and extend this argument further, and we can say that as the number of sides approaches infinity, the polygon actually becomes a circle. A circle is a curve, and a polygon does have sides, right? So if I increase the number of sides to a very large number, then the argument that I'm making is that the polygon will completely overlap the circle. There'll be no differentiation. You won't be able to differentiate between the polygon and the circle. Let me close the program first, and then we'll go back to our whiteboard. Okay, so now we are in our whiteboard, and now I think the statement that I've just made earlier will make much more sense, that a curve is nothing but a set of straight lines put together which are infinitesimally small. A set of infinitesimally small straight lines are put together, and it is making an illusion to be. So a curve is nothing but an illusion, you can say. So when seen from a broad point of view, the edges kind of just the edges kind of smooths out, and it feels as if it's a curve. But when you kind of zoom in, then you'll find that every curve is nothing but a straight line, just put together in a certain way. Okay. Now let's come to our. This is actually a very interesting thing that I'll discuss later, but let's focus on this thing first. The second thing that I want you to do is to remind yourselves the equation of a straight line, which is the y is equals to mx plus c. And let's forget the constant part, the intercept part, and focus on this. Y is equals to mx. So compare this equation with this equation and you will find a very striking coincidence, maybe very striking similarity between these two equations. Now, if I've just told you to compare these two equations, what deduction can you draw from the comparison? Now, the first thing that I can think of is differentiation gives you a function which gives you which outputs the equation of straight line at every neighborhood of x. This is what I would deduce, and this is what I wanted to share as well. So differentiation is actually breakdown of a curve into its parent straight line form. So what it does is it gives you the parental straight line equation for all of the x's, for all the neighborhood of x. And by that I mean that if I just focus on the zoomed in part, then this will be the axis, the x-axis. So what differentiation does is it gives you the line of the equation of line for all of these neighborhood of x, for all of these neighborhood of x values. So this is the neighborhood of x2, this is the neighborhood of x3, and so on and so forth. So differentiation breaks down your curve into its parental infinitesimal straight line form, and it provides you a function by which you can access those straight lines, by which you can access the equations of those straight lines according to the neighborhood where you want the straight line. I mean, according to the neighborhood where you want the straight line to be. So if I want the equation of straight line in the neighborhood of x1, so this is the point x1, and if I want the equation of the straight line in the neighborhood of the point in the neighborhood of the point x1, then this is the equation that I'll get. So if I substitute x1 in this equation, then I will get dy is equals to 2x1 dx. So this will be the equation of straight line. So the first literary difference that you'll see is the I'm sorry, I have written dx over here. So yeah, the first thing that you will notice is that this d factor is missing, right? So the d factor for me signifies that the lines that we're talking about, they're infinitesimally small. These are not just any line that we normally discuss. These are very small lines, and that's the small the d is the signature of that small aspect. That's why it's dy is equals to 2x dx. So differentiation, again, let me repeat the conclusive statement of what differentiation is. So differentiation is actually differentiation is breakdown of your curve into its infinitesimal straight line form. That's it. Breakdown of your curve into its infinitesimal straight line form, or you can say that differentiation breaks down your curve into its infinitesimal straight line form and gives you a function to access the equation of those straight lines based on the neighborhood of x where you want based on the neighborhood of x where you're willing to find the equation. Okay, so the equation will be divided based on the x neighborhoods, because as you know that uh, obviously it cannot be it cannot happen that uh, we'll say that what is the equation of line at point x. So we might say that x1 lies in this particular line, and we want the line where x1 point lies. This is what we can say. Or we can say that the line which is passing through the neighborhood of x. Okay, so the thing, okay, so it gives you the equation, so it gives you a function to access the equation of all those lines um, according to the neighborhood of x that you put in, right? So it gives you a function for the equation of all those straight lines, and the equation of all those straight lines is the function of x, or whatever that value can be. In case of parabola, it's a function of x. It's the function of the neighborhood value where you are finding the equation of the line, right? So what actually, so what we have actually done in differentiation is that we have broken down the curve into its infinitesimal straight line form, right? So it has become like this. All of them are straight lines actually, and these are neighborhood, and these are the straight lines according to the neighborhood values of x. Okay, according to the neighborhood of x. Okay, the straight line breakdown, so it's the straight line breakdown according to the neighborhood of x. So let's say this is the curve that you have broken down using differentiation. Now what integration does is, I think I don't even need to explicitly explain what integration does. It does nothing but it actually gives you cumulative equation of the curve which is being made by all those infinitesimal straight lines. So it integrates, it actually joins together all these infinitesimal straight lines, and it gives you the cumulative function of the curve which is being made by all those straight lines. So when you integrate, you get the function that you get, it represents the cumulative curve which is being represented by all of those straight lines put together. So this is what integration is. Okay, it joins together, and differentiation breaks down. So that's why integration is also called the antiderivative, because it's the opposite of differentiation. Differentiation breaks down and integration joins together. As I've told you, there's one interesting thing that I want you to observe, is that you might have just noticed that that sometimes in a curve there are some non-differentiable points. For example, this point is actually non-differentiable. Yeah, if you have studied non-differentiable points, then you will agree that you cannot differentiate this point. Now what differentiation does, as we have said, it actually gives you the equation of these straight lines, right? For all the neighborhood. Now what is it actually doing is it is just extending the straight line which was already there on both the sides. So let me draw another curve maybe, so that I can show you clearly what I mean. So let's say we are willing to find the derivative of x. We are willing to find the derivative of this function at this x neighborhood, let's say x naught. So the tangent, so you might have heard that differentiation gives you the tangent of a curve at a point. You cannot draw tangent. I mean, you can, if you know that if you have studied straight lines, then you'll be knowing that you cannot draw a straight line by just having one point, right? So you cannot draw tangent at a point on a curve because um, they I mean there cannot be such line which because there are actually infinite points. I'm sorry, there are actually infinite lines which can pass through a point. So when you say that we are drawing a tangent at a point on the curve, then what you actually mean is you are extending this line on both the sides in the neighborhood of that point, not at that point, but you are extending the you are extending the infinitesimal line in the neighborhood of that point on both the sides. And this point is non-differentiable because if you zoom in into this particular point, it is something like this, maybe. So if I ask you to draw a tangent at this point, there's no possible way you can draw a tangent using just one point. You cannot draw a line because to uniquely identify a straight line you need 2 points. Using one point you cannot draw a line. I mean there are actually infinite lines which can pass through this point. So the argument that I want to make is that these non-differentiable points are actually points, and the areas from where you can draw tangents are not actually points where you're actually talking about the neighborhood of that point. So we on a literal sense we say that we are drawing tangent at a point, but what we are actually doing is we are extending that infinitesimal line on both the sides in that neighborhood, in that neighborhood of whatever the interested or of whatever the point we're interested in. So if we are interested in this x naught point, then we are not actually drawing a tangent at this. If this point is x naught, then we are not actually drawing the tangent, or we are not actually drawing a line passing through this point. We are actually extending the line in this neighborhood, in the neighborhood of x naught on both the sides. And if you don't have this line there, likewise in this case you are not having this line, therefore there's no point of extension if you don't have a line already, right? Okay, so this is what I was saying. In case of tangent, when you say that differentiation gives you the tangent of a point on the curve, then it actually gives you the equation of this infinitesimal line extended on both the sides for that neighborhood of point, not that point, but for that neighborhood of that, but for the neighborhood of that point. So let me say it clearly once again, that when you say that differentiation gives you the tangent or derivative of a curve at a point, so derivative of a curve at a point gives you the tangent at that point, then what you actually mean is that derivative of that curve gives you the equation of the infinitesimal straight line extended on both the sides in that neighborhood of that point, not for that point, but in the neighborhood of that point, because you cannot draw a line given a point. But if you have a neighborhood, continuous of points. For example, if I have this neighborhood, very zoomed in neighborhood, so this is the x0 neighborhood, and if I have points in if I have some points in continuum in this neighborhood, I'm sorry, yeah, if I have some points in continuum in this particular neighborhood, then I can make a line, right? Then there'll be a straight line passing through this, passing through all of these points. But if you have a straight line and you're saying that I'm drawing a line, then I'm drawing using a point. I'm drawing a line on the edge of the curve, maybe. Then actually we're not actually defining it. We're not actually saying it correctly. The correct way to say it is the derivative of the point. The derivative of point gives you the extended equation of that infinitesimal small line in that neighborhood of point, of whatever point you're interested in. So if I'm interested in x0, then it gives me the equation of straight line. Then it gives me the equation of that infinitesimal straight line in the neighborhood of x0. x0 is my point of interest, extended on both the sides. Okay, so this is what it is. This is what I wanted to discuss about differentiation, integration, and see you in the next one.